Yes, I like it.
All right, so here is a curve in space. This is an interesting curve here. And we've got the TNB frame, right? We talked about the unit tangent, the unit normal, the unit binormal vectors. And those three form a little R3 coordinate system, right? Those are all orthogonal to one another. These vectors are all orthogonal to one another, and we know they have very specific directions relative to the motion. So do you remember which one of these would be T? So let's see. Let's slow this down here. Even more. There we go. So which one of these vectors would be T? Maybe you can see that they're red, blue, and green.
I know.
Which one do you think?
The red.
He wants the red arrow. Others of you agree? This is a good view of it.
Yes.
Yeah, so that red vector pointing like up and to the left right now, this vector right here, direction of motion, right? If we're in a car, that T vector is always pointing straight out the front of the car, no matter how the car is turning. Okay? And then we said the motion of the object is in the plane of T and which other vector determines the motion of the object? Yeah, the plane of T and N. So N is the direction of turning. So here's a good view right here. Okay, so we're going straight ahead. Straight ahead is our T vector. And then the plane of T and N is the plane of motion at that moment. And so the binormal vector is orthogonal to the plane of motion. So which one's the binormal vector? Blue or green? We have one vote for blue.
Second vote.
Yep. Yeah, so the motion right now, so you can see that the motion is somewhat vertical. We're heading forward in this direction, and we're turning what? To the left, right? Turning to the left. That's why this vector here is our normal vector. So the normal and the tangent vector together form the plane of motion. And then orthogonal to that plane to write its equation would be the binormal vector kind of coming out at us here, pointing towards us by the right-hand rule. All right, so this is called, these are the T, N, and B vectors. And they give a little 3D coordinate system that moves with the object. It moves with the object. And so to kind of reiterate that, you know, relative to the object, these vectors don't actually change relative to the object itself. They only change relative to the curve. So we can see that in this view, which is like us, it's like you're riding in the roller coaster somewhere. Where is it? So this is the same curve, but now we're sitting in the car here, and we're riding in the roller coaster, kind of. So the direction of turning is always up in this view. I would have preferred if they did the turning horizontal and the blue up or down binormal, but that's the way they did this. So so notice, so this is the curve. Here we are on the curve over here. And so they're adjusting the curve so that T is always straight ahead, N is always straight up, turning, and then B is always to the left. So following this curve around and then manipulating the curve so we always have this relative to the object, these vectors stay stationary. Okay, so questions on that? Thought that was a cool video to reinforce this idea of the unit tangent, unit normal, and binormal vectors. Any questions? Okay, I got another thing to show you here. So over here on the right side of the screen, do you see this thing that looks like a bouncing ball or something on a spring? Can you see that?
Yeah.
All right, cool. So at the top, let's talk about the, so position would be like the ordered pair where this thing is. And then if we took the derivative of position, we get velocity, right? So let's write these down. So position, that's dangerous. Let's do it over here. Position is RT. Velocity is the derivative, and that you just simply take the derivative of the individual components to get this new vector function, which is velocity. Speed is the magnitude of that. So this gives you a vector function. This gives you a real valued function, meaning you don't get a vector out, you get an actual number, that's the speed. So let's talk about at the top there. What about the speed at the very top? What's the speed at the top? What do we expect the value of this function to be at the t value at the top?
0.
0, right? It pauses for a second, right? So the object pauses for a second at the top, and so that means that the speed is 0, or the value of this function would be 0. Okay, what about the acceleration? So the acceleration is r double prime. So what about the acceleration at the top? Is that 0?
No, that's going to be negative, right?
Right, it's going to, at the very top, when it pauses, do you see that it's accelerating downward? Why? Because in this whole upper part of the path, it's getting slower on the way up and faster on the way down. So that whole time in this upper half, it's accelerating downward. Do you see that? All right, so what does that mean about the tangential component of acceleration? So we have a tangential component of acceleration, a normal component of acceleration. So if the speed it's slowing down and then speeding up there at the top, which of these values applies? Tangential acceleration or normal acceleration? Tangential. Okay, but now I'm going to tell you, you told me the speed is slowing down and speeding up here. I'm going to actually tell you that the speed of that object, it's actually staying constant. The speed of that object is actually uniform speed. How could this be?
It's in a circle.
So some of you might have picked up on this. Oops.
Are we viewing a circle from its edge? Yes, we are.
What I was showing you this whole time was actually an object going in a circle at a constant speed. So that acceleration that you were seeing at the top, was it tangential acceleration? What is the tangential acceleration of this object?
0.
0. If the speed is constant, which it is, then the tangential acceleration is 0 all the time. So, but you did see acceleration. I showed you by turning it on side. You saw that it was speeding up on the way, or slowing down on the way up, and speeding up on the way down, which means that at the top, it was accelerating downward. How is that possible? Because there are two components to acceleration, we know, right? There's this component in the direction of turning. There's acceleration just from the mere fact when an object turns on a curved path, there's acceleration, whether it's speeding up or slowing down or not. And so that downward acceleration was, I was really showing you acceleration due to turning, not tangential acceleration. Okay, does it make sense?
Yes.
Pretty cool, huh? So this just shows how just from an object turning on a curved path, there's naturally acceleration, even if it's not speeding up or slowing down. Okay, very good. So let's just go over the formulas one more time. So in the web work, it's more formula based. You're just using the formulas and cranking out answers. In lecture, we're focusing more on the concepts, and so all of it's important. All of it's important. If you need help with the algebra, I'm more than willing to help you through email and office hours to get through the tricky spots of the algebra if you need that. So I just don't spend a lot of time in lecture with just working through algebra. You guys have been doing this for years, right? Plugging into formulas and cranking stuff out. So I trust you can do it, and if you need help, I will definitely help you. Okay, so let's pause this, and let's take a look at, just summarize those formulas. Where are we? Yeah. So we looked at the different components of acceleration last time with these drawings, but let's just no. Here we go. So we said that if r is the position function with respect to time, then the second derivative is the acceleration. And just to reiterate one more time, acceleration of an object is due to two phenomena, speeding up and slowing down. What direction is that in?
Tangent.
Right. The direction of the velocity, r prime, which is the same as the direction of t. Okay? And then there's also acceleration due to turning. And I just showed you that when something turns, even if it's not speeding up or slowing down, if it's turning, it's accelerating. And what is that? What direction is that? N, right? Okay? So there's no, the motion, none of the motion is in the b direction. All the motion is in the plane of t and n. And that's why for acceleration, you have components in the tangential acceleration, tangential direction, and the turning direction. Okay, but you don't have any acceleration or any motion in the b direction. By definition, the Tn plane is the plane of motion. Okay, and so because t and n are exclusive from one another, they're orthogonal, so they share nothing in common. To get the total acceleration, or this r double prime, it's simply going to be the sum of those two components of acceleration. Right? It's components, right? Components sum up to the whole vector, and they're orthogonal to one another, right? Components sum up to the whole vector and are orthogonal. So when you talk about the tangential acceleration, you can talk about just the real valued part, which we'll do in a sec, or you can talk about it as a vector, right? So if you take the real valued part of the acceleration and multiply it by its corresponding direction vector, then you get the vector version of that acceleration. So we have two of those, add them together, and you get the second derivative, which is the acceleration. Okay, in your written homework, you work through a problem where you're going to find the second derivative using derivative rules and get that vector function. But then you're also going to find all of these, and then you're going to show that when you put it all together, when you actually do the math here and add them up together, you get exactly the same thing you get by taking the derivative twice. Okay, so that's an important thing to do for the homework. All right, so let's talk about those real valued acceleration components. So this is the tangential acceleration as a real valued function. So with the tangential acceleration, here we got all of the acceleration, the second derivative. Do we want as much of that as is in the direction of r prime, or orthogonal to r prime if it's tangential acceleration? Do we want to multiply these two in as much as they're in the same direction, or orthogonal to one another? So this is, we want the tangential acceleration. So how does this compare to the tangent direction? Same, right? This is the direction of t.
Same direction.
Yeah, same direction. This is the direction of t. So we want as much of this as is in the direction of t, or in the direction of the first derivative. Therefore, what will we have there?
Dot product.
That's dot product, right? Dot product was product of the magnitudes in as much as they're in the same direction. So we want the part of the second derivative that's in that direction, or the t direction. So we use dot product. Similarly with the normal, we want the part of this that's what? In this direction? It's the normal acceleration. We want as much of the second derivative as is orthogonal to that, right? So we want the direction of n is orthogonal to the direction of t. So what multiplication do we use here?
Cross.
We use cross product, right? Cross product is going to give us as much of the product of the magnitudes in as much as they're in orthogonal directions, so that would be the direction of n, and that's our normal acceleration. Now both of these, like I've been saying, these are real valued functions. Meaning, for any given value of t, you get a number back. You get a real value, right? Dot product gives a number. Cross product gives a vector, but you take the magnitude of it, that's a number. So these are the real valued versions of those two accelerations. If you want the vector valued versions, then you're just going to take this one times the t vector and take that one times the n vector. If you want all the acceleration, then you add it all together. And that's the same as the second derivative.
So I think you might be unmuted.
Did I mute myself?
No, I think its mic is unmuted this whole time.
So then these are vector valued. So you get the real valued versions, just multiply by their direction, their unit vectors in the direction, and you get the vector valued functions. Add them together, you get all the acceleration. Okay, so that will wrap up our little module here on vector functions and motion in space, which is the kind of most common application of vector functions. Any questions on that before we kind of change subjects?
Since they're real valued functions,
Uh-huh.
are they magnitudes? Or?
Yeah, these are numbers, right?
Yep.
This is the number that gives you like how much tangential acceleration you have, and this number gives you how much turning acceleration you have, just as a real value.
So it's basically a magnitude of change.
Yep, it's a rate of change of velocity, going forward and turning. Yep, these are both like rates of change of.
Can you memorize these equations for the next exam?
What's that? Yep, I think I do provide them. Yep.
Okay, thank you.
Yep. This one, no. That one I would not provide. That's a concept that's very important that you know that you could just write it down without memorizing it. But these two I can give you. Okay, let's shift gears. And let's talk about multivariable functions. Multivariable functions. So I've been using these terms, real valued function and vector valued function. So let's just kind of review that. Most of the function you've encountered in your math career up to this course have been y equals a function of x. Okay, this is a single variable real valued function. So when we say single variable, are we talking about the x or the y?
X.
That's the x. Single variable is the x, and then real valued means
Y.
the y. So it means you put a single variable gives values, input values, and then for each one of those values, the function generates a real value back, and that we call that y. Okay? So what about this function? So what would we call this? If this is a single variable real valued function, then what would these things that we've been working on be called?
Multivariable, multi-valued function?
Multivariable?
Single variable.
Single variable still, right?
Single variable, right?
Still single variable t. And then do we get a real value out of these functions? What do we get out?
I got a vector value.
We get a vector. So this is a single variable vector valued function. That's what we just finished up a week and a half, 2 weeks working on those, okay? Learning all about those.
I'm just assuming if it's multivariable, it would just be like f of x comma y or something like that.
Okay, and that's my question, yep. So what would it mean for a function to be multivariable? If these are both single variable functions, then a multivariable function means your independent thing is no longer a single value, but a combination of values, okay? And so if it's a multivariable real valued function, you have some combination of values that are giving a single real value. Okay, and so that's exactly what he was saying.
Would the surfaces that we were looking at last unit be an example?
Awesome, right, and we'll talk about that. Very good, excellent. All right, so what we got here is normally in terms of our x, y, and z, normally x and y are conventionally, so this is like a two variable real valued function, right? So multivariable, there's two independent variables. The function takes both of them simultaneously and spits out a real value for every given pair. Okay, so a good example of this would be, just a real world example would be like wave height. Wave height is a function of both wind speed and duration of time. So if everything's calm on the ocean, no waves, and a big gust of wind comes up for 5 or 10 seconds and then dies down again, what kind of waves do we get for that? Big or small? Yeah, maybe just the water will just ripple a little bit. Super small waves, right? But if that same wind gust blows for an hour without stopping, well, now we're going to start getting some choppiness, right? Some waves. And if that same wind gust blows for 5 hours, you're going to have big waves, right? So, and then if you have a very little wind, a very low velocity wind for a long time, that's going to, it may make some small waves, but not very big waves. So you see that the height of the waves at any given time is a function of both these things. It's a function of not only the wind speed, but how long the wind's been blowing. So that's a really good example of a multivariable real valued function.
Wouldn't it also be affected by moon position?
Sure, and so maybe there's a third variable. There are probably several other variables that affect wave height. So this is a pretty crude example, but yeah. So you could have other variables too that affect wave height. Okay, questions on that? Does that make sense? Just the introduction there. So whenever we're working with multivariable functions, they've got to be provided to us in some representation. There's got to be some way that we conceive or understand what the particular function we're working on is. And so we're going to talk about the different ways that these can be represented or put before us, right? Or that we could represent them. So representations. There are 4. The first is, so here, z equals x squared plus y squared. What was that? Does anyone remember what that was?
Ellipsoid.
Paraboloid.
So what were our surfaces? So let's write down our surfaces. We did planes first, or we did spheres first, and then planes. We talked about ellipsoids, paraboloids, cylinders, double cones. So this was our repertoire of surfaces. We're going to need them the whole rest of the course. So on exam 2, we're going to test on these again. You have to recognize them by their equation and then by their representation as a surface, right? These are our surfaces. So which was this? This was our reference.
Circular paraboloid.
Right. We spent about a half a day of class kind of expanding, breaking this down and kind of seeing how we got a paraboloid out of this. This is the reference paraboloid. And we know, like with paraboloids and double cones, we got 3 different kinds of transformations. We could like rotate the axis, do it on a different axis. We could change it to elliptical. So this is our circular paraboloid. We can make it elliptical. Or we could just move it, right? Translate it around. So we had those 3 transformations when it came to paraboloids and double cones. Ellipsoids were just basically a warped spheres, right? We could change one or more of the radii of a sphere to get an ellipsoid. Planes were there kind of, we worked hard on planes, they kind of stood alone. Cylinders, what were cylinders, right? So the easiest kind of cylinders is when you have an equation of 2 of the 3 variables, x, y, and z. So an equation of 2 variables is like a curve, but in R3, you let that sweep in the 3rd missing variable in that direction, and it sweeps out a cylinder, right? Okay, so now these surfaces, for instance, this reference paraboloid, we can see that as she mentioned earlier, we can see that as a multivariable function, right? So rather than write z, we could use our function notation here that says that this quantity, f of x, y, is a function of x and y taken together. So we could have any formula here involving x and y, and then that's a function of x and y. So this is the particular function that was our reference paraboloid. And this is our first representation. First representation would be a formula or function definition. So what does f of 1, 2 mean? What does that mean?
You plug in 1 for x, right? And 2 for y.
It means do something. Does it mean do something? Does it mean do something?
I would
That's a
say
very
so.
vague question.
Meaning, does that mean, is a command to you to plug in 1 and plug in 2 and solve it? Is that what that expression means?
When you plug in 1, you get 2.
The output's a real value.
Okay, so yes, it is equal to 5. That's what you get when you plug 1 in and 2, 5. But by itself, it stands alone as something meaningful, something that has meaning whether or not you calculate it to be 5 or not. Okay, it doesn't require you to figure out the number. This can have meaning in other expressions, other functions. We can use, this is called function notation, to represent, is it output or input value? Independent or dependent variable?
Independent.
This is a value of the independent variable, is that right?
Oh wait, no, the entire thing's the output, so that it's dependent, but what's inside is the...
So the whole thing is a value of a dependent variable.
Dependent variable. Yeah.
It's the value of the dependent variable, and it tells us exactly which value of the dependent variable it is. It's the value of the dependent variable when the independent variables are taken as 1 and 2. Okay? So when x is 1 and y is 2, this thing represents the value of the dependent variable of this function. And we can use that. We don't have to calculate it. There's no mandate, there's no requirement to plug it in and get that. Now, if you need the value, yes, of course you can plug in the 1 and 2 and get it, but it stands alone as its own meaningful thing, which is the value of the dependent variable of f when x is 1 and y is 2. So it is not a requirement to do something necessarily. Okay. Next. So that's the first representation that you'll be given or you'll have to come up with related to one of these multivariable functions is a formula or function definition. Okay, next is a graph in R3. So how does this thing graph in R3?
It extends in the positive z direction.
What kind of thing is it? So let's talk about in R2 when we had single variable, single variable real valued function. Our customary way, a convention, is to have that x-axis, that horizontal axis, be values of the independent variable, and then for every one of those, the function gives us a value of the dependent variable, f of x, and that's shown as height above or below the x-axis. Let's say this is x1, f of x1. x2, f of x2. Etc. x5, f of x5. So ordered pairs, the value of the independent variable is shown horizontally, and the value of the dependent variable is shown vertically as a y value. And then if you let x vary continuously through the real numbers, if the function is defined for all those, then you get a smooth curve, right? You get a curve, or a continuous curve. You get a continuous curve, and those are all points of ordered pairs of a value of x and a corresponding value of f of x according to the function. So what about in R3? So in R3, we keep the same kind of thing going on here with R3. We keep the independent thing horizontal, right? So this is the convention. It doesn't have to be this way, but conventionally, we've got what? Independent on the horizontal axis. Now we have the independent is ordered pairs on the xy plane. So x1, y1, x2, y2. So we're taking pairs of values together, etc. So you got all these points in the xy plane. Okay? And for each one of those, we get a value of the function according to the rule, and that value then is a height right above or below that ordered pair that generated that function value. So this is why when we first introduced the R3 coordinate system, and maybe we thought it should have been like this: x, y, and then let's throw z this way. Since it's our new axis, z, we'll do it this way. So why didn't we do that? Why isn't it that? Because we're keeping the same kind of convention that our independent thing is horizontal, right? So horizontal axis. Now horizontal plane is where our independent ordered pairs lie. It's kind of like the launch pad. And then the dependent quantity is always shown, not always, but conventionally shown by height. So now here that was y, right? Y values were the values of the function shown by height on the graph. Same thing here now. Values of the function, which are z, are shown by height. So z3, z1, z2, etc. Or f of x2, f of x2, y2, f of x3, y3, f of x1, y1 are the z values in the graph, the height. And so if you take all the ordered pairs in the region of the horizontal plane and get all the ordered triples from their corresponding heights, what kind of graph is formed by that? Imagine getting heights and ordered triples at every coordinate pair xy in the horizontal plane. And what are we going to get?
A surface.
Yeah, it's going to be a surface, right? It's going to be a surface. Like whatever, you know. And so we kind of knew that already because we're just replacing now our function notation with the dependent variable z. And we know that single equations of x, y, and z make surfaces, right? We've hammered that, right? These are our surfaces. So now we can make multivariable functions out of these by letting z be the dependent variable. Or x or y. Actually, so we can make x be the independent variable. We could have a dependent. We can have say a single cone that opens in the y direction, and then y is a function of x and z. And that would be fine too. But so conventionally though, z is our height, and that's our dependent variable as we graph those surfaces in R3. Okay, is this making sense so far? So those are the first two representations. We can represent it as a formula, a function definition. We can represent a graph in R3. And then there's another kind of graph we can use to represent these multivariable functions. I'm going to clear this drawing here. And that is, if we go back to our traces, remember we learned traces. If we use z values for the traces and graph a bunch of level curves, it's called what's actually contour plot. We make what's called a contour plot. A contour plot. So let's see the contour plot for our reference paraboloid here. And actually we already made this a week or so ago. 2 weeks ago.
Oh, is that the one that has the whole bunch of
Yeah, and I don't want to give it away here. So
paraboloids right in front of each other?
Share.
You have a paraboloid.
Turn this off here. Okay. Forgot to reset my file there, so let's see. Okay, so am I sharing again? Here we go. So this was for our reference paraboloid. Z equals x squared plus y squared. So this is z equals 5. So to get level curves, we set z set to constants. And so at z equals 5, if we choose z equals 5, then we're talking about where does the surface intersect the plane z equals 5. And what curve do we get for that? We get 5 equals x squared plus y squared, which is a circle of radius square root of 5. And so that's a level curve. That's a level curve. When you take many level curves such that your z increment stays the same, it forms a contour plot. So my z increment here is just 1. So here's z equals 3, 2, there's 1. There's equals 3, 4, 5, 6. There's 8, so there's z equals 8 and the respective circle. So we're going to plot all those at the same time. So this is z equals 9, and that's the circle of radius 3. Here's all of them from 9, 8, 7, 6, all the way to 1. So this interior circle right here, that's z equals 1. That means that every point, so every point has some coordinate pair, x and y, and if it's on the contour line, the level curve, for z equals 1, then x squared plus y squared equals 1. So that is z equals 1. And every point gives a value of the function of 1. Every point on that curve. And then similarly, 2, 3, so this one here. So this one right here. Every point, every xy coordinate pair that's on that circle has a z value in the function of 4. And then similarly out here, this is for z of 9. Every point on that curve would be an x and y taken together that would give you z equals 9. Okay, so what does it mean? So let's see them all there. So all right, so these are the level curves then shown in R3. But so the contour plot is where you take those level curves and just smash them down against the xy plane. You put all those in the xy plane, and you get a representation of the surface, or the function, like that. Okay, so what does it mean when the curves are close together. What does that mean for the function?
So the height is increasing really fast.
Yeah, good. So for the same horizontal change, so imagine making a horizontal change, say, of 1 unit. A horizontal change of 1 unit in the xy plane. See how many lines you cross there? So every time you cross a line, you are increasing your z by that much, in this case 1. From here, if I do the same, look, if I do the same change of 1, say near the origin, I only crossed 1 line. Here I crossed like 4 or 5 lines. So when the curves are close together, a horizontal change or a change in your x and y variables is going to mean a rapid change in z, or a large change in z. So a high rate of change. Because you're crossing lots of z values for the same horizontal change in the xy plane. And so that means a steeper surface. So that all that I wrote there is for this situation here. Here, I have a low rate of change. For the same horizontal change, I only cross 1 z. My z doesn't change very much. And so the surface is more shallow. And we see that with the surface itself. So if I turn on the surface, near the origin, it's more shallow. For the same horizontal change, you don't see much change in z. You get further away from the origin, for the same horizontal change, your z changes a whole lot, right? So you're going to cross lots of lines. And so your z is going to change much more. And so that's higher rate of change. Okay, does that make sense?
I'm just wondering, if you wanted to get parabolas, would you instead plug in for x or y and then just plug in?
Yeah, but then that would not be, those wouldn't be level curves. So a contour plot is necessarily level curves. Level meaning values of z. Okay, so one more quick, the last representation is pretty quick and easy, and that is a table of values. So create a table of values, okay? So, and I'll just show you that in a second here, but just to recap, there's 4 main representations for these multivariable functions. The first is a formula or a function definition, okay? That's right here on the right. F of xy equals x squared plus y squared is an example, right? The graph in R3, in this case, for that example, is the paraboloid. Traces of the z values, the level curves, gives you that representation, a contour plot, a contour plot. And finally, a table of values. So here's how the table of values works. Pretty self-explanatory. For different values, you got different values of x and then different values of y. And so you're taking values of x and y together, and every pair of an x and y together gives you a z. So the values inside the table here are the corresponding values of z, or f of xy. So for instance, f of 1, 2 is 5. Right? F of 1, 2 is 5, like we talked about before. F of 3, 0 is 9. So all 4 of these are going to be the main representations that we work with when we're working with these multivariable functions. And we start doing calculus, right? There's no calculus that we've talked about today with these, just simply representing these types of functions. So
in that table, is y horizontal?
Mm-hmm.
Okay, just like if you were looking down from the z direction.
Looking down from the z direction.
Looking down.
Yeah, like
above.
yeah, I guess so. I guess yep. So this would be like your x-axis this way, and then your y-axis this way. Yeah, you could think of it that way. Mm-hmm.